Hello there, and then welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at perfect squares and then its identities. We look at the meaning of perfect squares, generate some few perfect squares, and then we see perfect squares in relation to odd numbers. How do we get perfect squares even from odd numbers? And we'll also look at some identities that we can use to evaluate perfect squares of binomial expressions. Without much ado, let's quickly look into it. So when we talk of perfect square, what do we mean? A perfect square is a number that can be written as the square of an integer. So simply put, perfect square is equal to, we said, the square of an integer. So if you want an integer to be n, and then its square is what we have over here. Hence, if n is equal to 1, then our perfect square, n squared, would then be 1 times 1, which will be equal to 1. If our n is equal to 2, then it implies our n squared is equal to a 2 times 2, which is equal to 4. If our n is equal to 3, then we are going to have n squared, which then becomes 3 times 3, which is also equal to 9. We can proceed on and on and on. And these numbers that we generate here are what we call the perfect squares. So simply put, a perfect square comes from multiplying a number by itself. So as you have seen we obtaining here, we just multiply the numbers by themselves, 2 by 2, 3 by 3. Hence, for the first 10 perfect squares, we have 1 times 1, which gives us 1. We have 2 times 2, which gives us 4. 3 times 3, that gives us 9. 4 times 4, we have our 16. 5 times 5, 25. 6 times 6, 36. 7 times 7, 49. 8 times 8, we have our 64. Then 9 times 9 gives us an 81. Then 10 times 10, which also gives us 100. This set is the first 10 perfect squares. Every number is a perfect square. From what you see over here, every number here is a perfect square. Now let's relate this to algebra. Perfect square also appear in algebraic forms as well. Now, how do they appear in algebraic forms? So if you have a binomial such as x plus 3 all squared, the result you get here is a perfect square. Because how is it going to be obtained? It is obtained from multiplying this by itself. So x plus 3 multiplying an x plus 3. If you remember, we said a perfect square is obtained by multiplying a number by itself. This here, we have x plus 3, and it is multiplying itself again. Hence, our result becomes a perfect square. Not only can you use binomial, but then monomials can also give us perfect squares. So if you have 2x all squared, that also gives us what? 2x times a 2x. And that is also a perfect square. A minus b all squared. It becomes a minus b multiplying itself again. And these are all perfect squares. So how do we identify if a quadratic expression is a perfect square? A quadratic expression is a perfect square if and only if, when it is factorized, the two factors you get are the same. So for instance, this we have over here, that is x squared plus 6x then plus 9. If you have to factorize this, it gives us x plus 3, then x plus 3. Now, as you can see, if we are to rewrite it, it becomes x plus 3, then another bracket, x plus 3, which is x plus 3 all squared. The term is going to multiply itself. You see, it is only this that we can then confirm that this quadratic expression we have here is a perfect square. Why? Because its factors, when factorized, are the same. So it is important to take note once again that a quadratic expression is a perfect square if it comes from squaring a binomial. As simple as that. Now, the last thing we'll be looking at is odd number patterns, how they relate to perfect squares. Talking of odd number patterns, let's first of all write out some few perfect squares. So we had 1 times 1, which gives us a 1. Then 2 times 2, which gives us a 4. Then we had 3 times 3, which gave us a 9. Then 4 times 4, we have our 16. And 5 times 5, which also gives us a 25. What we want to do here is to sum up all the odd numbers we know. So for the very first odd number, 1, and 1 is equal to 1, right? Now the next odd number, let me just write down our odd numbers here so that we can easily make reference to them. So odd numbers. So we have 1, then 3, 5, 7, 9, 11, 13, 15, and then it goes on and on and on. So if we take just the first one, we have 1. If we add the first odd number to the second odd number, what do you see? It gives us the second perfect square. Let's add the first 3 odd numbers and see. That is 1 plus 3 plus 5. That gives us a 9. So that is 1 plus 3 plus 5. And if you continue to add 7 to, you are going to get a 16. So 1 plus 3 plus 5 plus 7. If you have to add the 9 as well, you are going to get a 25. So 1 plus 3 plus 5 plus 7 plus 9. Do you see what is going on? So we will then get a pattern whose general rule is for every perfect square that is n squared, then if we want to actually add odd numbers to give us that perfect square, then it is the sum of the first n terms. The sum of the first n odd numbers. Or you can use the summation symbol to write it as n squared is equal to your sigma I being what? 1 to n. You have your xi, where x is odd. You see, as simple as that. This is a pattern that relates the sum of odd numbers to perfect squares. Now, why does the odd number pattern works? Let's look at why it works. I'll give you a visual representation. The square numbers always form squares. If we say the perfect squares always form square, this is what we mean. So we know the first perfect square is 1. You see, I can form just, this is a square, and I can use just one box to form that. That is fine. Now, what if I want to use 2 boxes? As you can see, this is not going to be a square, but rather I will need to add 2 more to it to form my square. You see that? And that makes 4. Now, how many did I add to this? So initially, we had just 1. But now, we are adding 1, 2, and then 3. That is, we want to make sure the previous one it's surrounded fully. Now, if I want this to also be surrounded fully, then I'm going to add 1 here. I'll add 1 here. I'll add 1 here. And then I'll also add 1 here as well. Now, if I want this to be surrounded fully, then I'll have to add 1 here, 1 here, come down to the next stage, then add 1 here, and then add 1 here as well. What does it mean? So if I take this first one, what I'm going to do is I'll add 2 more to its side and then come down again to add another 2 more down here. But that isn't enough because this square is there empty. Hence, I'll need to add 1 more to be able to form my square. So in total, how many have we added? 1, 2, 3, 4, 5. That is what keeps happening. We started with 1. We needed to add another 3 to cover this 1. And then we need to add another 5 to cover the previous one. We would also need to add another 1, 2, 3, 4, 5, 6, and then the corner here, 7. And you'd realize that it is just repetition or a pattern that keeps adding odd numbers. Now, if we are to speed it all up, this is what is going to happen if we still want to be consistent with forming the squares. Each layer will add an odd number of squares to surround the previous layer. So on that note, we'll end this lesson here. But as usual, I'll give you some exercises so you try on your own. So here are just 4 exercises you can try on your own to test your understanding. The very first one says, which of the following are perfect squares? So you go through them, then tell me which of them are perfect with reason. Then you have to state the sum of the odd numbers that give you 16 and then 36. We've gone through that. Now the next one says, expand and identify the perfect square x plus 4 all squared. So I've told you that for algebra, if you have the binomial and it's squared, the answer you have becomes your perfect square. Then which of the following expressions is a perfect square? You can only tell if you factorize. So if you factorize and then it looks something like this, that is a term squared, then that makes it a perfect square. This is how far this lesson is going to go. I do hope it was helpful. If there's any issue of concern, you can always let me know at the comment section and I'll address that for you. See you in our next lesson and bye for now. Stay safe.